Hello chemistry students. In this final video on module 15, we'll be looking at the last section starting on page 546. And first we're just going to review a couple of these principles that summarize the effect of temperature on equilibrium considering Le Chatelier's principle. So we know when temperature is raised in a system, the equilibrium will shift away from the side that has energy. So in this exothermic reaction, the energy is on the side of our products, and when we raise the temperature, the equilibrium will shift toward the reactant side. As in contrast, right, we have this endothermic reaction. The energy is on the reactant side, and when the temperature is raised, it would shift over to the product side. Now, alternatively, when the temperature is lowered, then the equilibrium will shift toward the side that has energy. So if you cool this one down, the equilibrium shifts over on this side. If you cool this one down, it's going to shift over on this side. So in light of those principles, we'll look at example 15.6. We have the combination of hydrogen and fluorine gas. We're given our delta H of negative 273 kilojoules. We know from this negative, right, that this is an exothermic reaction, and that, whoops, I lost my pen there, and that the energy would be considered a product in this side. Okay, so if you can imagine that that our energy is over on this side, then we can ask the question, what will happen to the concentrations of each substance when the temperature is raised? All right, so we know if temperature is raised, the equilibrium shifts away from the side with the energy. So in this case, it's going to shift in this direction toward the side of the reactants. In that case, this side would decrease the hydrogen fluoride, and these would increase. Now, in B, it says what will happen to the concentration of each substance if the temperature is lowered. So when the temperature is lowered, then the equilibrium shifts toward the side with the energy, and in this case, it would switch toward the side with the products, and this hydrogen fluoride would increase, and then these two gases, the hydrogen and fluorine, would decrease. Okay, let's look at on your own 15:10. There's two parts to this. This is the first part. It says, consider the following reaction that has already attained equilibrium. In this case, our delta H is 132 kilojoules. We know automatically when we have a positive delta H, the equation is endothermic, and in this case, the energy is going to be on our reactant side. So it says, what will happen to the amount of calcium carbonate, this reactant, if the temperature is raised? So we know from our previous examples, when it's heated, the equilibrium will shift away from the energy side. So it's going to go over to the product side in this case. And when that's shifted, it means this will be consumed and this will decrease, and then these two would increase. Now the second part of this problem or question, it asks, what will happen to the concentration of the carbon dioxide if the temperature is lowered? So once again, it's the same equation. It's endothermic. Energy is going on our reactant side. When the temperature is lowered, the reaction shifts toward the side that contains the energy. This will cause these two to be consumed and the concentration goes down, whereas this would increase and go up. Okay, then our module moves on to acid and base equilibria. And just to review, we know an acid is any molecule that donates a hydrogen ion, whereas a base is a molecule that accepts a hydrogen ion. And so what we were looking at first here is what's called the acid ionization reaction. And that is the reaction in which the hydrogen ion separates from an acid molecule so it can be donated in another reaction. So a summary of this would be like hydrochloric acid with hydroxyl groups yields water and chlorine ions. So what the book explains is that even though this is one equation, it actually happens in two steps. The first step is with the hydrochloric acid, the hydrogen ion dissociates and it forms a hydrogen ion and a chlorine ion. So the HCl, hydrochloric acid, breaks down into two components. And then the second step, the hydrogen ion is then received by this hydroxy group, and then that forms the water here. So to proceed further and to look at more quantifying this type of reaction, we look at what's called the acid ionization constant. And this is actually a number. It's an equilibrium constant, K, for an acid's ionization reaction. And what this is going to help us understand is the strength of an acid. So just to sort of generically start here, they show this equation. The lowercase a, b, and c are again our stoichiometric coefficients. And then here the HA, the capital H and A, stands for an acid that's all together. The hydrogen is still bonded to the rest of the molecule. But then as it dissociates, you have the hydrogen ion alone here, and then this would be the ion that's created after the hydrogen is taken off it. Now, we determine the strength of an acid with this formula. It's very similar, obviously, to the K formulas that you worked with earlier in the module. And so you're basically looking at these products here of the dissociation, their concentrations, right, with their raised to a certain power, and then it's divided by the concentration of the original acid, also raised to a certain power. So the K with the A subscript refers to the acid, the A refers to the acid ionization constant. And as these are quantified, these Ks in general, the larger the K, the stronger is the acid. Okay, so let's just look at an application of that. This is just the formula repeated here. And we're looking at this equation of acetic acid dissociating. So here you have the C2H4O2 dissociating, one of the hydrogen ions comes off, forming a hydrogen ion, and then here you have the ion that's left. So we're taking the two products here, and they're in the numerator, and then we have the reactant here is down in the denominator, and in this particular equation, all the coefficients are just 1, so everything is just raised to the first power. So this equation also follows for a base ionization constant. And so again, we're just applying it to the same formula. And we just like to point out first that because the H2O is in liquid form, it's dropped from this equation. Because remember, liquids and solids we don't include in that. But we do take these products, the ammonium ion and the hydroxy ion, and they would go in our numerator. and then this NH3, the ammonia, is in the denominator, and then because this is for a base, it's a lowercase b here, so it's K for the base, and then that's the rest of the equation. Okay, let's look at example 15.7. It has two parts on page 549. It says nitrous acid, which is HNO2, has an ionization constant equal to 4.5 times 10 to the negative fourth molarity. Give the equation for this ionization constant. Is this acid stronger or weaker than acetic acid? And then it gives the K for that. So here we have the formula, right? We're given HNO2, and then we know that the hydrogen would have to dissociate in order for this ionization reaction to occur, and then would form this other ion here, this negative ion. So these are our two products that are then put in the numerator, and then the reactant is in the denominator, since it's K of A because it's for an acid, and this is sufficient for the answer for this question. Then if we have to compare it numerically, right, 4.5 times 10 to the minus fourth, right, is actually a higher number, but that, in this case, it means it's a slightly stronger acid than acetic acid. So that's how they're just comparing these two numbers here. And so this is just simply a numerical evaluation. It is greater or less than. So a higher number, this is to the negative fourth versus 10 to the negative fifth. This would be the stronger acid. All right, let's look at the second half of this problem. This says methylamine, which is CH5N, is a base with the K of the base of 4.4 times 10 to the minus fifth. Give the equation for its ionization constant. Would this be considered a strong or weak base? So first we have to come up with the equation. We would add this base, right, to water, and then look at how it forms this hydroxy group and this ion here. And then we take these two products and put them in the numerator, and this reactant, and put it in the denominator. Everything's got a 1 as a stoichiometric coefficient, so that is all that we need for our exponents there. And then the final comparison is comparing, or just asking whether or not that's considered a strong or a weak base. It's somewhat relative, but because this is such a small number, then it's considered a weak base. All right, let's look at on your own 1511. What's the equation for the acid ionization constant of this HClO2, that's chlorous acid? So first we know that the hydrogen, right, is going to dissociate from this other part of the molecule. And then now that we have it dissociated, we know these two parts would go in the numerator, with the brackets around them being the concentration of, and then the reactant would go in the denominator. Okay, what on your own 1512, what's the equation for the base ionization constant of this pH3, which is considered phosphine? We know if it's a base, it must accept the hydrogen ion, and we basically start by just taking this molecule, adding it to water in the liquid form. It's got to this has to receive a hydrogen ion, so it goes from pH3 to pH4, and then the water turns into a hydroxyl group. Then we take these two products. They're going to be put in the numerator, and then this goes in the denominator, and this is disregarded because it's in the liquid phase. All right, just a review on the pH scale, right? It says it's called the pH scale because the letters stand for potential hydrogen. And at least in this program, you should definitely know 7 is always neutral, and when you go below 7, that's considered acidic, and when you go above 7, that's considered basic. This can also be called alkaline. And the farther that you get from the 7, the stronger the acid would be. So the lower the number, the stronger the acid. And in this case, the higher the number, the stronger the base. So they categorize here. It says solutions with pH 0 to 1.9, so that would be 2, are considered strongly acidic. One example here would be battery acid or gastric acid, that's in your stomach. Solutions with 2 up to just before 7, 6.9, are considered weakly acidic. That's considered soda. They have even here acid rain, black coffee. And then pH of 7 is neutral. Then we're going to verge into the basic end. Solutions from 7 to 12, they consider weakly basic. So that has here seawater, baking soda, milk of magnesia, and ammonia, which we worked with in our lab. And then from 12 to 14 are strongly basic. Those are things that would really hurt your skin if they touch you. So that would be bleach is one considered here. And I actually can't, I know drain cleaner is 14. So that's super basic. Okay, so let's look at on your own 1513. Each equal concentration aqueous solutions are made with the following 4 chemicals. The pH of each solution is written next to the formula. So we have the C6H6OH, it's at 3.2. So that's phenyloxonium. And then this one is potassium hydroxide. The pH is 12. This is C2H7N, dimethylamine. The pH is 9. And then hydrogen bromide, the pH is 0.5. So it says identify the acids and the bases. So the first thing you look at here is you want to say what's greater than 7 and what's less than 7. So anything less than 7 is going to be an acid. So here we have the hydrogen bromide, that's less than 7. That's a strong acid because it's so low. And then the other acid here is the C6H6OH. That's a pH of 3.2. The book considers that a weak acid. Then the bases are greater than 7. So we have the C2H7N, the dimethylamine, that is pH 9. It's considered a weak base. And then the other base, the potassium hydroxide, is at 12, and that's considered a strong base. All right, so the last part of this module discusses the existence of acid rain, which is caused by pollution. However, the author mentions it's been improved over the last 40 years due to improvement in government regulations that's lowered air pollution. But they've documented that some rain has been as low of a pH as 3.2. So just to talk about how acid rain is formed, they point out that rain naturally is slightly acidic due to the way that carbon dioxide in the air combines with water to form some carbonic acid. I mean, it's not obviously not all rain is all carbonic acid, but there's enough that does react, so naturally the rain pH would be about 5.3. But we have, through industry, actually lowered that 5.3 even lower at times from different products in the air. For example, when we burn coal, the coal can have sulfur contained in it, and when that is combined in the atmosphere, you have the sulfur trioxide combining with water to form this sulfuric acid. And then automobiles and other gasoline burning engines will emit nitrogen dioxide, and then when that combines with the rainwater, you can get nitric acid and nitrous acid forming in the rainwater. And so they just point out that that has occurred, but as I mentioned, it's definitely improved over the last 40 years. All right, that wraps up Module 15, and I will be posting some study guide answers as well.